Differentiation using the chain rule. In this lesson, we're going to look at finding derivatives of functions that are a little bit more complicated than the simple functions of x that you've been doing in the past. You will have already experienced finding derivatives similar to this first example. Find dy dx of y equals x to the fourth. Of course, most students find this real simple. Dy dx, using what we call the power rule. You recall we take this exponent and it comes down in front as a multiplier, so we'll have 4. And then we write our x and we subtract 1 from this exponent, giving us a 3. So dy dx is 4x cubed. As I said, this is an example of our simple power rule for finding the derivative of powers of x. If we have x to the n power, then we get n times x to the n minus 1. Let's talk a little bit about what exactly our notation means. What does dy dx actually mean? I mean, you know that it's a symbol to mean the derivative, but it specifically is saying find the derivative of y with respect to x. This is indicating that y is a function of x. So that might mean that we have powers of x, or we might have a trig function where x is the argument of that trig function. But this notation is specifically indicating what our independent variable is that we're taking the derivative with respect to. Now, what does y prime mean? We use this notation a lot. We use this as a shorthand notation for dy dx. So in this notation, we know that we're finding the derivative of y, but it is not explicitly stated what our independent variable is, in this case x. Now, what does dy du mean? Well, this means the derivative of y with respect to u. In other words, y is a function of u. What does du dx mean? It means to find the derivative of u with respect to x. In other words, u is a function of x. I wanted to review this notation because we're going to look at what we call composite functions. You might recall from algebra what a composite function means. A composite function, you recall, is indicated f circle g of x. This notation means composition. If you have f circle g of x, that means you are finding f of the quantity g of x. In other words, the function g of x gets inserted into the structure of function f. For example, to review that idea, given that f of x is the square root of x and g of x is 3x plus 2, we're going to find f circle g of x. Okay, so f circle g of x, as I said, means f of the quantity g of x. One thing I like to remind students in this order, f is the function on the outside, and notice it remains on the outside. G is the function on the inside, and g becomes the inside function here. I say that because recall, if you see g circle f, this is reversed, g of f of x, and you get a different solution. Now, usually when you have sets of parentheses, you start on the inside and work out, don't you? So we're going to replace g of x with what it's equal to. So replacing g of x with 3x plus 2, I now have a notation that says find f of 3x plus 2. So this is indicating go to function f for your structure. So in function f, I see that I have a square root. And of course, remember, anything inside this parenthesis is a replacement for the variable in function f. So this variable x is being replaced with this 3x plus 2. So the composition f circle g of x gives us the square root of 3x plus 2. Now what's the major difference? Well, notice function f is just a real simple square root of a simple x. Whereas here we have a square root of a function of x. It's more complicated. This is going to give us the idea of how we find derivatives. Now, we're going to start with this example. We are given that y equals u squared. Notice y is a function of u here, not x. And then we also know that u equals 2x plus 1. In other words, u is a function of x. So y is a function of u, and u is a function of x. And notice we want to find the derivative of y with respect to x. Okay? Y is not a function of x here. I'm going to do this problem a couple of different ways, but for now, I'm going to start here, and I'm going to say, okay, if y equals u squared and u is 2x plus 1, I'm going to replace the u here with what it's equal to. So y would equal, in place of u, 2x plus 1, and notice u is squared, so y equals the quantity 2x plus 1 squared. Now I have y as a function of x. Now in this format, I don't know how to find the derivative because I need simple powers of x to do that. So what I'm going to do is simply square this binomial. Recall, to square a binomial, you square the first term. That would give you 4x squared. Then you multiply the first and second terms together, getting 2x, and you double that answer. So 2x doubled gives you 4x. And then finally you square the last term and get a plus 1. Now if you don't remember that shortcut process for squaring a binomial, you can write two factors of 2x plus 1 side by side and do the FOIL process, and you'll get the same thing. Now I have y written out in the familiar format that we've been doing derivatives, and I can find that dy dx equals, okay, when I bring this 2 down and multiply times 4, I get 8x. Notice when I subtract 1, my exponent here will be 1, plus the derivative of 4x is just 4, and notice, of course, the derivative of 1 is 0. So dy dx equals 8x plus 4. Now, we can certainly do this with small powers here, but what if this had been something like, say, to the 10th power, and I had put the 2x plus 1 here, but this was to the 10th? Do you see that doing the algebra to multiply that out to get simple powers of x would be a really long process? So what we'd like to do is to be able to come up with a way to find dy dx without every time having to multiply this out. So I want to show you something else. I want to underline this because remember, this is my answer. Let's go back up here to y, and let's find dy du, the derivative of y with respect to u. Now in that case, I have a simple power of u, and so the derivative is going to be 2 times u to the first power. Okay? Now, since u is a function of x, I'm going to find du dx. In other words, the derivative of u with respect to x. Okay, so if I'm taking this derivative with respect to x, the derivative of 2x would be a 2, and the derivative of 1 would be a 0. Now, I want to show you what happens if I take dy du and multiply times du dx. Well, dy du is 2u, du dx is 2, so I get 4 times u. Notice, if I replace u with what it's equal to, the 2x plus 1, I have 8x plus 4. Notice exactly the same answer that we got here. So this is indicating that if y is a more complicated function of x than just simple powers, I can find the derivative of y with respect to u times the derivative of u with respect to x, and the end result is the derivative of y with respect to x. Now, if you come back to this notation, remember this notation is not exactly a fraction, but sometimes we do treat it sort of like one. Notice if I thought of these as being fractions, dy du times du dx, the du's would sort of cancel out and leave us the dy dx. If you'll keep that in mind, that will help you as you go about doing some of these derivatives. Now, let's look at what we call the chain rule. And I have it in the form we just looked at it. dy dx equals dy du times du dx. Now, every time that you see a composite function it is not always written out initially in this format. So I want to show you an alternate form of this chain rule that looks a lot more complicated. I really like this form because it's simple and straightforward. But notice here, the derivative with respect to x of f of g of x. In other words, f is a function of this function here. It's going to be a little more complicated. Notice, according to the chain rule, you find the derivative of f where the argument of f is still g of x, and you multiply times the derivative of this function g that was placed inside there. Now I'm going to go back to the example that we just did a minute ago, and we're going to do this another way. Y equals u squared and u equals 2x plus 1, find dy dx. First, I'm going to rewrite as we did before, replacing u with 2x plus 1, and I'm going to have the form y equals 2x plus 1 quantity squared. Now, this is a composite function. This function has been placed into the function x squared, if you will. So, to do this derivative using the chain rule without having to do the two separate pieces, we're going to look at this as I have a power of something. Now, this something is a lot more complicated than a simple x, so that indicates I need to use my chain rule. But I have a power function. Notice the last operation that would be done is a power. So I'm going to do the power rule. So I'm thinking power rule here. Okay, so dy dx will equal. If you do a power rule, you bring the exponent down, and then whatever you had to that power, you write down, and you subtract 1 from the exponent. So notice when I bring the 2 down, whatever was to the power I recopied, I subtracted 1 from my exponent and got a 1. Now all I have done at this point is the power rule. Now here is where the chain rule comes in. Because this was more complicated than a simple x, the chain rule says find that derivative of that inside function. So the derivative of this inside function, in other words, the derivative of 2x plus 1, would be a 2. So I did the power rule, the 2 came down, my function was reduced to power, and then I go inside and take the derivative of that inside function. Notice if we multiply this out, 2 times 2 is a 4, times the 2x plus 1 gives me the 8x plus 4, which is exactly the same answer that we had a while ago. Now, keeping this in mind, we're going to look at what we call the general power rule. Notice this says find the derivative with respect to x, but you'll notice here it's not x to a power, but it's rather u to a power. Anytime we see the u here, and this is an x here, this is indicating that this is more complicated than just a simple x probably. Now look at your general power rule. Notice it starts out the same. Your exponent comes down, n. Then this quantity is written down, and you subtract 1 from your exponent. So this is the usual power rule part. Then you'll notice over here at the end you see u prime. In other words, take the derivative of that function that is raised to that power. Now, having looked at this general power rule, we're going to look at a number of examples where we indicate how to use this chain rule. Now, I'm going to caution you that most students, when they start out, either don't quite go far enough or they go too far. They get a little bit confused about that chain rule. So we're going to try to really be specific about how the chain rule operates as we do these derivatives. Notice it says to differentiate y equals the quantity 3x squared plus 2 to the 5th power. Now it didn't say specifically, but anytime you have y as a function of x here, we're going to find dy dx, or if you prefer, you can use the notation y prime as a shorthand notation for that. Now here's what you need to look at. Looking at this thing right here, the last operation that would be done is this outside exponent, isn't it? Because of the parentheses. You would do what's in here and then do the exponent. That indicates that this is a power form, okay? Indicating I need to use my power rule. So my power rule says I'll bring this exponent down in front as a multiplier. Now be careful to recopy exactly this function that was raised to a power. Notice I'm not changing anything. 3x squared plus 2. 5 came down. I recopied my function that was raised to a power. Now I'm going to subtract 1 from this power. So that gives me a 4. Now my chain rule part says go inside this parenthesis and take the derivative. So we've already done the power rule, so we're through with this part here. But going inside and taking the derivative inside, I'm going to get a what? 2 times 3 is 6x to the first power. Of course, that would be plus a 0. So we're going to multiply by 6x to the first power. Notice again on this general power rule, I want to make this specific. Your n comes down, your quantity is reduced to power, and you multiply times the derivative of that function that was raised to a power. So we've done all those pieces. Now we usually simplify. Now recall your order of operations. I cannot multiply 5 times the quantity in here because of this exponent. Remember, exponents happen before you can multiply. So the only way I could multiply by the 5 is after I've raised this to the 4th power. So instead of doing that, what we will usually do is we'll take the 5 times this 6x, which notice is to the first power, so there's no exponent to be done. We'll say 5 times 6x is 30x, and then we'll just bring down this quantity, 3x squared plus 2, to the 4th power, and we will leave our answer in this format. We don't want to have to raise that to the 4th power and get that complicated polynomial. Okay, well let's look at this example. Find f prime of x for f of x equals the 4th root of x cubed minus 4x. Now, I'm going to start off by simply rewriting my function in a different format. Recall, if you have roots, you can indicate those roots by using fractional exponents. So instead of saying the 4th root of x cubed minus 4x, I'm going to take the quantity x cubed minus 4x to the 1/4 power. Remember, your fractional exponents indicate a root. This has this thing written in a power form. Notice I have a function of x to a power. So we will use the power rule first to get the derivative. The power rule says we're going to bring this exponent down 1/4. Then remember, we recopy this function exactly like it is, but we subtract 1 from the exponent. Well, 1/4 subtract 1 is going to give us a negative answer, negative 3/4. Now, this is where the chain rule kicks in. We go inside our parenthesis and take the derivative inside. Well, the derivative inside is going to give me what? 3x squared minus 4. Okay? Now, at this point we have the derivative, but we're going to do some simplifying. Now, this is sort of the standard simplification that is expected. First of all, we generally do not leave negative exponents. But recall that all a negative exponent has you do is to put that quantity as 1/4 that. So this is 1/4 times 1/, the quantity x cubed minus 4x to the positive 3/4 power, times the quantity 3x squared minus 4. And of course that's over 1. Notice there's no negative exponent that causes us to flip that one. So we have a product of these three things. Now, all we're going to do is multiply this out, which gives us 3x squared minus 4 on top. Notice 1 times that. And on the bottom we will have the 4 times the x cubed minus 4x to the 3/4 power. And generally we will leave that in this notation. Now, I do not always write this step down. Usually I realize this is going to flip upside down because of the negative exponent. So this goes down in the denominator with the 4, and since this does not have a negative exponent, it stays up on top. Now, you will sometimes see this answer written back in radical format. So I'm going to do that just to illustrate we would have a fourth root of the quantity x cubed minus 4x cubed. I just wanted to review that. Remember, you have a 3/4 power. This is your root, and then it's to that power. I usually do not write this form here. I usually leave my answer here, but your professor may prefer this, so I wanted to show you both possible solutions. Now that we have looked at this general power rule, which basically is the power rule together with the chain rule operating, we're going to look at some other functions, and we're going to be bringing in some of the other rules of finding derivatives as we do these functions. Notice this says find g prime of x for g of x equals 5 over 7x plus 5 to the 8th power. Now actually there's two different ways that you can do this problem. There's one that I prefer, and here's what I look at. Notice in this fraction format that the numerator is simply a constant value. There is no x, no variable up here. When that is the case, I usually like to rewrite my function by bringing this quantity up and writing it with a negative power. So in other words, I'm going to leave the 5, and I'm going to write 7x plus 5 to the negative 8 power. Now, I don't always do that if this is a variable, and I'll show you another example in a second that's a little bit different. But if that's a constant, I nearly always will write it this way. That's because finding the derivative is now simply using the power rule together with the chain rule. If you leave it in this form, you have to use a quotient rule, which is pretty long and complicated, as you might remember. So let's do the power rule. The negative 8 will come down, and since we have the 5 in front, we'll multiply those. 5 times negative 8 gives us negative 40. Then we're going to write our quantity, 7x plus 5, subtract 1 from our exponent, which gives us negative 9, and then remember the chain rule part, we come inside and take the derivative of this function inside. The derivative of 7x plus 5 is a 7. Okay? Again, we now have the derivative, but we're going to simplify. Remember, this quantity that has the negative power, we want to flip over and put it in the denominator. So negative 40 times 7 is negative 280. And then we're going to flip this down on the bottom, 7x plus 5 to the 9th power. Now, I might want to mention here, just remembering your rules, as long as these are all multiplied together, then this will just come down and it will end up being underneath the things that are not moved underneath. Okay? This example, I want to look at another example that is very similar to this one, but one that was, I'm going to use the quotient rule this time instead of rewriting like we did last time. Let me show you the difference here. I'm going to leave this last example. Notice here we had just a 5, whereas in this example I have a 5x. See, this is just a constant, but this is a function of x. And so usually if this is a function of x, I go ahead and do the quotient rule to find that derivative. So let's take a look at this one. I do want to rewrite just a little bit on this function before we start doing the derivative. All I'm going to do is to rewrite this radical in a power format. So f of x is 5x over the quantity 2x minus 1 to the 1/3 power. Now, for emphasis here, I want to write down that we're doing the quotient rule here, because notice I have a fraction bar here. This function is being divided by this one. You'll need to keep in mind as you do the derivative that you're doing the quotient rule. This is one that's rather complicated and you can get lost if you're not real careful, so I'll be coming back from time to time reminding you of the quotient rule. The quotient rule starts denominator times derivative of numerator, doesn't it? So let's write our denominator, 2x minus 1 to the 1/3, times the derivative of the numerator is a 5. Denominator, derivative of numerator, minus the numerator, 5x, times the derivative of the denominator. Now here is where it gets complicated, because when you look at this denominator, notice it's one of those complicated power forms. So to get the derivative of the denominator, we'll bring the 1/3 down. Then we will write the 2x minus 1, subtract 1 from this exponent gives us negative 2/3. And then chain rule, come inside, the derivative inside is 2. Now this is a lot of times where students start getting lost. We did denominator, derivative of numerator, minus numerator, derivative of denominator. This is where we did the power rule and the chain rule. So don't forget that too. Okay, all of this, remember the last part of the quotient rule, over denominator squared. Now I might want to remind you, if you take 2x minus 1 to the 1/3 and you square that power to a power, so you multiply those exponents and get 2/3. So this was going to be over 2x minus 1 to the 2/3 power. Now let's just stop for a second, make sure we have everything. Denominator, derivative of numerator, minus numerator, derivative of denominator, denominator squared. Okay, now that we have the derivative, we've got some simplifying that we need to do. I'm going to, first of all, just do a little bit of rewriting to make this a little bit more simple format. Notice here I have the quantity 2x minus 1 to the 1/3 times 5. I can eliminate some of my parentheses by putting the 5 in front. So let's do that. 5 times 2x minus 1 to the 1/3 power. Okay, after my minus sign here, notice this is all multiplied together, but this one has a power on it. So we can say 5x times 1/3 times 2. Okay, well 2 times 5x is 10x times 1/3 gives me 10x over 3 times the quantity 2x minus 1 to the negative 2/3. And then all of this is over the 2x minus 1 to the 2/3 power. Now, doing that just sort of gets everything in a place where I can get it together and start worrying about how else I need to simplify this problem. Now, there's two things that still need to be done for sure. One is I have a negative exponent here, and the other is I have a fraction up here in my numerator. I need to take care of both of those. I like to go ahead and get rid of that fraction next. So if you have a fraction, we have a big fraction here. Here's the numerator, and here's the denominator of my big fraction. I can multiply these by the same thing. I'm going to choose to multiply by 3 so that when I distribute this 3, I'll knock out this fraction right here. So let's do that first. 3 times this gives me 15 times 2x minus 1 to the 1/3 minus, the 3 will cancel this 3, so I'll have 10x times 2x minus 1 to the negative 2/3, and then this is going to be over 3 times the 2x minus 1 to the 2/3. Do you see what we've done just to clear out that fraction? Okay, so that's taking care of one of our problems. Now the next problem is this negative exponent. I want you to be sure and understand that this time I cannot take this quantity and simply drop it down here in the denominator because of this subtract right here. Everything, it has to be times everything in order for you to move it down. This is times the 10x, but it's not times this. So we're going to handle this differently. We're going to do some factoring. Okay? Now, I have this 2x minus 1 to a power in both of my terms on either side of this subtract. So I know I can take out a power of 2x minus 1. I also noticed that I could factor out a 5, but usually this first time I only worry about this complicated part right here. So let's take out a power of 2x minus 1. Now you might recall that when you're factoring, you always factor it out to the smallest exponent. Well, if you compare 1/3 and negative 2/3, remember negative 2/3 is smaller than 1/3. So we're going to factor this out to the negative 2/3 power. Okay? Now looking at our first term, I'm still going to have a 15 here. Since this power is different from this one, I know I'm going to have a power of 2x minus 1 here. Now you've got to figure out what this exponent is. One way is to take the original exponent here and subtract the exponent that you're factoring out. 1/3 subtract negative 2/3. Notice that changes signs. You get a plus, so you get 3/3 or 1. I'm going to put the 1 down for emphasis. So 1/3 subtract negative 2/3 gives me a 1 here. Another way to look at this is if I were multiplying this back out, when I multiplied these, I would add these exponents. So this needs to be a 1 because added to negative 2/3, that gives me my 1/3 here. So in any case, you need to understand that that's a 1 right there. Now, in the second term, minus, I've got the 10x, and because this is the power that I factored out, that factor is completely gone, and I don't have that any longer. Now, this is over my 3 times 2x minus 1 to the 2/3 power. What this has accomplished by doing that factoring, this is now times everything else in the numerator, and I can now move it down below. So let's come down in the denominator. I'm going to write the denominator down first. I already have a 3, a 2x minus 1 to the 2/3 power. This I'm going to move down here and change the exponent to a positive. So 2x minus 1 to the positive 2/3 comes down here. Now we're going to simplify this. Since this turned out to be a 1, I can now distribute my 15 across here. So 15 times 2x gives me 30x, minus 15 times 1 is 15, and then I have minus the 10x. Okay, now 30x minus 10x gives me 20x minus the 15 over 3 times the quantity, 2x minus 1. Notice since these are alike and I'm multiplying, I can add those exponents and get 4/3. So I have 20x minus 15 over 3 times 2x minus 1 to the 4/3. Now, I usually leave my answer like this. However, you could, if you want to, factor a 5 out of the numerator and write it as 5 times 4x minus 3. Sometimes that's a good idea just to be sure that something doesn't cancel. And if you prefer, instead of leaving this in a fractional exponent form, you could go back to radicals. It's a cube root, notice, because of that. 2x minus 1 to the 4th power. Now, I generally don't, as I said, don't write this radical format. I usually leave it like this. But your instructor might prefer the radical format. Our next example is to find the derivative of f of x equals x cubed times the square root of x squared plus 2. Now, again, I'm going to rewrite, instead of in a radical format, I'm going to use the power form. So we have x cubed, then we have the quantity x squared plus 2, that will be to the 1/2 power. Now, it's going to be very important that you see, again, the format. Notice x cubed is what? Times the x squared plus 2 to the 1/2. If you were doing this problem, if these were numbers, you would take the square root of this quantity, cube this quantity, and the last operation you would do is to multiply. It's important that you understand that, to realize that this is a product of two functions, and so you need to use the product rule as your overlying rule in finding this derivative. Now remember, your product rule says first times derivative of second plus second times derivative of first. That's what we're going to do here. My first function is x cubed times the derivative of my second function. Well, if you look at this second function, do you see that complicated power format? So power rule with chain rule. 1/2 comes down. X squared plus 2, we'll subtract 1 from that exponent and get a negative 1/2, and then we have to go inside. The derivative inside is 2x. So I have the first function, the derivative of the second function, plus my second function is x squared plus 2 to the 1/2 times the derivative of my first function, 3x squared. Okay, again, make sure we have everything. First, derivative of second plus second, derivative of first. Now we're ready to simplify our answer. This is a product here. X cubed times 1/2 times 2x. Well, notice the 1/2 times 2x would give us a 1x times x cubed would be x to the 4th times x squared plus 2 to the negative 1/2, and then plus I have 3x squared times x squared plus 2 to the 1/2. Okay? Now again, I'm not through because I have a negative power that I don't want to leave. Again, this is not times everything. See our plus sign here? So I can't just move this underneath everything. So again, we're going to do some factoring. I'm going to take care of this complicated thing first. So x squared plus 2, negative 1/2 is smaller than positive 1/2, so I'm going to factor out negative 1/2 power. So in this first term, since I'm factoring this out, I will have x to the 4th. Plus, in the second term, I'm going to have a 3x squared, and I will have a power of x squared plus 2. Now, what's the power? Well, 1/2 subtract negative 1/2 gives me a 1. Or you can think 1 added to negative 1/2 gives me 1/2. So this is to the first power. Now that this is times everything, we can move it underneath. So we will have x squared plus 2 to the 1/2 in the denominator, and in the numerator I can do some simplifying. I can distribute here. That will give me 3x to the 4th plus 6x squared, and then adding like terms, I have 4x to the 4th plus 6x squared over x squared plus 2 to the 1/2 power. Again, you can leave your answer here, or if you'd like to factor your numerator, you could factor out a 2x squared. That would give you 2x squared plus 3 as your second factor over x squared plus 2 to the 1/2. Again, either of these answers is good. A lot of times the reason for the factoring is to be sure that what you get here wouldn't cancel with one of the factors that you have here. Okay, find the derivative of y equals the quantity 4x minus 3 over x squared plus 1 all to the 6th power. Again, look at your format. All of this is to the 6th power. So this is a power rule format. So as we do our derivative, our exponent is going to come down in front. The quantity 4x minus 3 over x squared plus 1 will be now to the 5th power after we subtract 1 from our exponent. And then here's where the chain rule comes in, and we come inside. Now, if you come inside, you'll notice that you've got a quotient. So as you come inside, you're going to be doing the quotient rule, okay? So let's see if we can keep up. The quotient is the denominator, x squared plus 1, times the derivative of the numerator, which is a 4, minus the numerator, 4x minus 3, times the derivative of the denominator, 2x, all over the denominator, x squared plus 1 squared. Now let's stop a second and see where all this came from. Power rule, 6 came down, my quantity is reduced to power. Then go inside because of the chain rule. It's a quotient. Denominator, derivative of numerator, minus numerator, derivative of denominator, over denominator squared. Now, we have finished our derivative and we're ready to simplify. So I'm going to write my 6 as 6 over 1. And I'm going to choose to split this up now as 4x minus 3 to the 5th over x squared plus 1 to the 5th. And then we're going to do some simplifying on this part. Distributing my 4, I have 4x squared plus 4. And then here, notice your negative, so I'll have an 8x with a negative, so minus 8x squared. Negative 6x, but this negative will change that to a plus 6x. And this is over x squared plus 1 squared. Now I think you'll see here why I wanted to split this up, because as I multiply, these are alike, and I can add the exponents. So I have a 6, 4x minus 3 to the 5th. combining my like terms here, I've got a negative 4x squared plus 6x plus 4. All of this is over x squared plus 1 to the 7th power, adding my exponents, 7th power. Now, I'm going to go ahead, since I have a common factor here of 2, and I'm going to choose to multiply or bring out a negative 2 so that this will be a positive leading term here. So we're going to factor a negative 2 out of this and put with this 6 out here. So we'll get a negative 12 out front, 4x minus 3 to the 5th. And since we're factoring out a negative 2, this will be positive 2x squared minus 3x minus 2. Now I'm going to do one more step just to be sure that I can't reduce, because I think this will factor perhaps. So let's see, we've got negative 12, we have 4x minus 3 to the 5th, and let's see if we do 2x and 1x on this trinomial. I think if we put a 2 here and a 1 here, let's see, let's make that a plus and a minus. Do you see we've got 2x squared minus 4x plus 1x is minus 3x, and we get our minus 2. I wanted to do that factoring just to be sure that I did not get a factor that would perhaps cancel with something down here. So since it turns out it wouldn't cancel, I could have stopped here, but it's usually a good idea to go ahead and factor when you can to be sure that you've got everything reduced as much as possible. Now I might mention on this problem, instead of doing it the way that I have shown you here, you could rewrite this function as 4x minus 3 to the 6th power over x squared plus 1 to the 6th power and do a quotient rule. I have found, though, that for me at least, this seems to work out a little bit faster and quicker than going through that quotient rule. But there's certainly not anything wrong with doing the problem that way if you'd like. Now at this point, I'd like to sort of shift gears a little bit. We've done a lot of problems where we've used that general power rule, which is basically a combination of the power rule and the chain rule. And we've looked at, of course, incorporating product rules and quotient rules as well. But I want to turn our attention now to trig functions. Just as we can have complicated powers, we can also have complicated trig functions. And when we have those, then we're going to have to employ the chain rule as well. Let's take a look at some formulas. Derivatives of trig functions. Now I first wrote the familiar one. The derivative with respect to x of sine x is just cosine x. You probably remember that. But let's look at this formula I've written. Notice we're still doing the derivative with respect to x. But instead of saying sine x, it says sine u. As before, that u is indicating that this is probably a function of x here that is the argument of the sine function instead of just an x. You'll notice on the derivative we start out the same way as we did up here. The derivative of a sine function is the cosine function. And I want to emphasize, notice the u. The argument is the same. Then, if this is not just an x, this is where the chain rule part comes in, and we multiply this cosine u by the derivative of u with respect to x. That's similar to going inside on those power forms. Similarly, the derivative of cosine x we know is negative sine x. So if we have a complicated cosine function, the derivative with respect to x of cosine u is negative sine u, but then we attach times du dx. The derivative of tangent x, recall, was secant squared x. So again, if this is a u, it's a complicated function of x here, we'll do secant squared u, same argument, and attach that times du dx. Now, I did not write out all of the other formulas in the u format, but I did want to write them down just to recall. The derivative of cotangent x is negative cosecant squared x. So if this is complicated, it would be a u, this would be negative cosecant squared u du dx. The derivative of secant x is secant x tangent x. The derivative of cosecant x is negative cosecant x cotangent x. Okay? So, let's take a look at some problems. Find the derivative of y equals sine 5x. Notice the argument of my sine function is 5x. It's not just a simple x. So that's, if you will, that's my u that we're talking about. It's a more complicated form. What I want you to realize here, though, is that this is basically a sine function. So the derivative of a sine function is a cosine. The argument here stays the same. Remember, it started out saying cosine u. Then we multiply times the derivative of u with respect to x. Take the derivative of this argument. The derivative of 5x is a 5. Now, I've been referring to this argument of the trig function. I want to just emphasize to you right now that the only way that you ever change the arguments of trig functions is using trig identities. So you don't multiply things by them, you can't factor stuff out of them, move in front, and they don't change when you find derivatives. Okay, so we've done the derivative of sine u, or sine 5x, is cosine 5x, times the derivative of the 5x. Now, again, to simplify, we're just going to put this 5 in front of that cosine function, 5 cosine 5x. The 5 is times the cosine function, it's not times the argument. Find the derivative of y equals the cosine of 3x plus 2. Notice that's in parentheses, so all of this is the argument of our cosine function. It's much more complicated, isn't it, than just an x. So if we're doing the derivative of a cosine function is negative sine. And again, this argument, notice, is not changing. I'm just writing that argument down exactly like it was. The derivative of a cosine is negative sine, same argument. Now, because this is more complicated than just an x, we'll use that chain rule here. The derivative of 3x plus 2 is a 3. And then we'll rewrite this as negative 3 times the sine of 3x plus 2. Find the derivative of g of x equals the tangent of 4x. Well, this is a tangent function. What's the derivative of a tangent function? The derivative of a tangent is secant squared. So we're going to have secant squared 4x. And then the derivative of the argument is a 4. So 4 secant squared 4x. Find the derivative of f of x equals sine cubed 2x. Now, I want to emphasize here notation. You might remember from trig that when you have a power that's written between the name of the trig function and the argument of the trig function, it means the trig function itself is being raised to a power. In other words, that is a short way of writing the quantity sine 2x to the third power. So, the important thing to notice here is this is a power form. It is something to a power. So you're going to use your power rule to start your derivative. So your power rule would say you'll bring your power down in front, then your sine 2x would be reduced to power, so it would be down to the second power. And then your chain rule says, okay, come inside and take the derivative inside. So when you get inside, you see sine 2x. Well, the derivative of sine 2x is cosine 2x times 2. Now, this is usually the place where students quit a little bit too soon. You do the power. 3 comes down, sine to the second power. Come inside. The derivative of a sine is cosine. And then because this argument is more complicated than just an x, you take the derivative of the argument. Actually, you're applying the chain rule twice here. Do you see that? Power rule, chain rule says come inside, and then chain rule says take the derivative of that argument of that trig function. So, at any rate, we have 2 times 3 is 6, and I'm going to write this as sine squared 2x, so I don't have to use the parentheses on it, cosine 2x. Now, my next example looks real similar, so let me just kind of slide this down. F of x equals sine 2x cubed. I wanted to do this just to emphasize the difference in notations. Do you see your exponent here is not between the trig function and the 2. And so it is not the sine function that is being cubed. It is only the x that is being cubed. Now, the only way that this could mean the same as this is if you had parentheses around sine 2x. So, as we do the derivative of this example here, it is not a power, but it's simply a sine function. So, to get f prime of x, the derivative of a sine function is cosine with the same argument times, this would be your u, the derivative of that argument is a 6x squared. Okay? So 6x squared times the cosine of 2x cubed. It's real important, as I said, that you understand the notation because it makes a big difference. Here we basically had a power form. Here we just had a simple sine function. This completes the examples that I have for you on using the chain rule. I hope that you have found this helpful, and I hope that it clarifies some of the problems that you're having. I do want to emphasize really work on some of those things like factoring out negative exponents and clearing complex fractions and recognizing the basic form that you're going to have to use when you find the derivative.